everything. That way, if you're not able to be here the whole time or you just want to hear stuff again, that will be fine. I haven't figured out for sure where the videos are going to live, but I know for sure that everyone who's here will have access to them. So we're working out the details of what's allowable. And let me describe the setup that we have in here. So we have what I refer to as roomers and zoomers. Roomers are OOMERS. We have 1, 2, 3, 4, 5, 6 of those and about 20 or so zoomers. I know you guys can't see each other, but you can hear each other. And I have one screen of zoomers in front of me, and then I have a screen that I'm going to share. And the only thing that's going to be captured by the recording is my shared screen and our audio. So none of your pictures, including mine, will be anywhere in the video. Because I have two screens, that also means that I can watch the chat window if you'd like to send questions or comments that way. Or you can feel free to ask questions or provide comments at any point. You're not interrupting me. I want this to be as useful and, I guess, personalized as we can make it. Given the fact that there's 30 of us in here, that's a little bit of a challenge, but we'll make it work. So let me, one thing, I'm going to turn on the transcript, so if anyone wants to watch my words get mangled by the Zoom translation algorithm, then we'll do screen share so that we can all see each other, or see the thing that I'm saying. Okay, Zoomers, can you see my screen and hear me okay? Everybody's good? Roomers. That's a test to see if we're awake yet. You all passed. All right. So let me tell you a little bit of the backstory about my approach for doing workshops. I first tried to teach myself longitudinal modeling in approximately 2002. I was working as a graduate research assistant in the Lifespan Institute at the University of Kansas. And I was in the unit of research design and analysis, where we were in charge of helping people with their data, writing analysis plans for grants, and helping to write papers and do analyses and all that kind of stuff. And my supervisor, who was a very nice woman and taught me a lot of things, handed me a book. The book was Snyder's and Bosker's multi-level analysis book from 1999. And she said, I need you to learn how to do growth models. Read this. So I don't know if you're familiar with this particular book, but it's all about clustered data. So it's all about kids in schools as the topic of the multi-level analysis. And I'm reading through this at the rate of about a page a day, thinking, when do I get to the growth curves? Because this is not what I signed up for. Why did she give me this book? And then finally, like in chapter 8, it's like, oh, by the way, time is nested in person, and you can do that too. And I spent a lot of time trying to figure things out, a lot of time working with the notation and trying to understand the ideas that were behind the notation, because I could hardly keep the symbols straight, let alone the concepts. And it wasn't until I had the chance to audit a class as a postdoc at Penn State, where I was the person with my hand in the air about every 30 seconds asking questions, because I was finally starting to put things together as the professor was going over at Microvine. And then I went to a few more workshops. And then by some stroke of, I'm going to go with luck/bad decision making, the people at Penn State let me teach. And so I wanted to teach a class on multi-level analysis. I learned it 10 minutes ago. This is going to be fine. And it was that first experience of trying to explain it to other people that made me realize how little I actually understood. And I'm still working my way through it. But my approach to the way that I teach this is I try to give the introduction I wish I would have had. Because I don't start very well from let X equal, right, as your starting point. I start with concepts, words, and then we bring the notation and the equations in. So that's my approach, for better or worse. That's the way that I wrote the book. The book that I wrote a couple of years ago is designed for people who are trying to teach themselves as well. So the first part of this is a lot of words and a lot of concepts, because there's a lot of overlap in the way that people approach longitudinal analysis from different perspectives, and I want us to start to understand how they sync together and when they differ and why. So does that sound like a reasonable plan? Okay, cool enough. For those of you who are where I was, where you've learned a little bit about this stuff and you're trying to put things together or you're trying to understand it better, this will be more useful to you than for someone who's hearing this for the first time. But for those of you who are students here, I've got good news. I'm teaching this class in the fall, And for the first time in about 5 years, I'm going to be teaching the advanced second half of it that I haven't gotten a chance to do at Iowa. So if this all seems like a lot for 1 week, and it will be, you'll get to hear it again. And for those of you who aren't students, my classes live on YouTube. So you're welcome to hang out virtually with us, watch the videos at your own leisure, and try to pick things up and put them together as you need. So that's my plan. So any questions, comments before we jump in? Ready to do this? All right. Let's see, it is 9:09. I think maybe a break around like 10:15, 10:30, somewhere in there. Mm-hmm. At least 15 to 20 minutes so you can get some coffee or stretch your legs or answer emails, whatever you got to do. All right. Away we go. So in terms of specifying how longitudinal information can relate across pieces of variables, two very important concepts that you will hear come out of my mouth repeatedly is this distinction between what is between persons and what is within persons. And if you start a longitudinal study with one occasion of measurement as a cross-sectional study, then you automatically have between-person variation. That's what you would have had to begin with, differences between people. Some people are higher, some people are lower, you don't know why. The extra piece of information that longitudinal research and designs can bring you is the idea of within persons. And so there's a distinction in the language that I use for this. It's about individual change as opposed to individual differences. So you're not just looking at differences between people, but how people change relative to where they started. And that can take a lot of different forms. If you want to sound fancy, you would use the terms inter-individual differences to talk about between persons, and the term intra-individual differences to talk about within persons. And if you're giving a job talk, you can start to throw these words around like, I'm going to examine inter-individual differences and intra-individual variability, and it sounds way cooler than between person versus within person. I thought I enabled the transcript. I'm sorry, must have hit the wrong button. Okay, so now we got the transcript going, we got the recording going. I have my caffeine on board, clearly. I need to slow down. I just get so excited to be back talking about this stuff. It's so much fun. So we have both of these sources of variation in here and interactions of the two. So if we have people that differ from other people in how they change, then that's between person differences and within person change. So it gets tricky to keep the language straight, but these two different levels of analysis are what we have to pay attention to. Because just because we have longitudinal data doesn't mean that we'll make the right longitudinal conclusions unless we can separate out these two different sources of information. I tend to use the word person as the adjective, but any type of sampling unit that is measured repeatedly is what I'm talking about. So if you're doing longitudinal research on schools, for instance, then school would be your person. If you're looking at organizational behavior, then companies or businesses would be your person. So does anyone think of another adjective that I might be missing? Person good? Good enough? Okay, person's good enough. Oh, yeah, now I have to hide the transcript because it's going to say things like Rambo when I say Rimmel, and then I'll just giggle, and that's not good. All right, moving on. Another way that I think about different kinds of longitudinal data is whether or not you're expecting systematic change over time or just within person fluctuation. And very rarely is it a clear-cut case of only one and not the other. So I think of these more as a continuum. So if you're doing a long-term longitudinal study where the point is to see how people change and perhaps how they change differently as a function of some treatment process or other type of between-person variable, then I would call that within-person change. And the type of analysis that lends itself to that most readily is what's known as growth curve models. Interestingly, even if people decline, it's still called growth. And even if their change is described by a line, it's still called curve. So that's just the language that people use. It's growth curves. The latent part is if you've estimated the same model using structural equation modeling software instead. But we'll get to a lot of that in this workshop. So the key idea here is that, like on the picture on the bottom, if people change differently, then the total variation of an outcome over time has to change with it. People spread themselves apart, the variance increases. So one of the big things we'll have to make sure of is that our model can adequately track that increase and decrease in variance across time, as well as the corresponding increase or decrease in covariance across time between the occasions. So that's one type of design. On the other end of the spectrum is what I would call within-person fluctuation. And when I was first starting to teach this, we called these daily diary studies. Now the term is ecological momentary assessment, for instance. And here, time is not really of interest. It's just a way to get a lot of information about a person as to what's happening during those occasions. What's their mood like? What's their stress like? What's their health like? What's their cortisol like? What is their blood pressure like? What is their A1C glucose readings like? Things like that. So it's not so much that it's Tuesday or that it's time 2, it's just what's going on at these occasions. And so this is my attempt at a picture of what that type of data would look like. Here, even though you could plot the responses across time, you wouldn't really see a pattern. So the best fitting line might actually be a straight line indicating no change as a function of time, but change as a function of other stuff. But there's still plenty of room for individual differences. So these are my PowerPoint drawing squiggles. The blue person here is higher than everyone else all the time. The red person's kind of in the middle, and the green person's at the bottom. So there are cross-sectional between-person differences that are observable in within-person data. But then there's also like this purple person here. What's up with them? So there's individual differences in volatility that can also be tracked in those types of data. So if you think about the idea of a person being moody, right? Not just in a bad mood or a good mood, but moody means that they are very subject to fluctuations in mood, or consistency or inconsistency, those sorts of ideas. So there's a lot of different types of longitudinal designs. There's a lot of different questions, but this sort of categorization as to which section you're in tends to be useful in guiding what type of analysis framework is going to be most useful. So does this strike a chord with anyone who has real data that they're interested in? Yes, a few nods. Anyone want to share what type of data they're thinking of? No one wants to share. Please. Okay, we got Jared, then Lisa. Go for it.
So I have reading data for kids, and I was looking at a bivariate model. So I have words correct per minute and accuracy. I wanted to look at, I was kind of thinking about doing an autoregressive model, bivariate autoregressive model, to see if those two things can predict the next data point. But yeah, so I have like 1,000 kids with up to 36 data points.
1,000 kids, 36 data points. How frequently are those 36 data points measured? Weekly. So should they be getting better at reading? As measured by speed and accuracy? Mm-hmm. So then that's sort of on the growth curve page, but because you have so much information, there'll be a lot of fluctuation around the growth curve for each person.
Yeah.
And so you were looking at sort of how one's ability at a given occasion affects some other variable at a subsequent occasion, that kind of thing?
Yeah, I was thinking like, if you measure both of them, because usually you only measure like words correct per minute, but if you look at the accuracy, can that help us predict how kids are going to kind of grow? Then that's what I was kind of thinking.
Okay. So you have then a design that kind of captures both of these aspects at the same time. One thing that I will warn you about that we'll talk about in much greater detail on Thursday is the need to make sure that your model has this within-person change part built into it before you look at how this occasion predicts the next one. Because kids could be related in their speed and accuracy. What's the other thing you're trying to predict?
I was just looking at just like how can we use our previous data points to predict the next data point.
Oh, okay.
So an auto-regressive.
Gotcha. So the same is true. Because if you think of it as a time series type of problem, where you're looking at autocorrelation and other sorts of time series types of phenomenon, The assumption that you would have to make for that to work is that the data are stationary. And if someone's growing, that's the opposite of stationary.
Okay.
So that's the one trick with that type of data, is keeping track of the change component separate from the autoregressive component, because the autoregressive component will pick up on the change component.
Okay.
If that makes sense.
Yeah.
Yeah, we'll get there. We'll get there. Thank you for sharing. Lisa, where are you? There you are.
I'm here. I'm also looking at words read correct per minute data for an intervention, Data Mountain, which teaches students to look at their own data. And I have 30 sessions. The RCT that I did this year is just half of it, so I have 54 kids in 3 conditions. And previously the intervention was 15 sessions long, and now it's 30. So I'm also curious to see if the growth of the first 15 sessions is different from the growth of the second 16 to 30 sessions.
Okay. So would the idea be like, can you get by with 15, or do you really need all 30?
Yeah, with number one, it's very variable data because the probes are different difficulties no matter what the people do, but also, at some point I feel like these kids, especially because they're students with disabilities, that they're going to flatline at one point, they're going to reach their potential with the program, and they're not going to grow without another intervention in place. So I'm kind of curious to see if the back half of the program is at a lesser slope than we see the climb at the beginning.
Okay. So as put a pin in it for you, what you're sounding like to me, it would be a piecewise growth model, where you're deliberately fitting separate slopes to each section of the data, and you can test whether the growth rate in the second half is different than the growth rate in the first half, as well as potential continuous versions of that, which would be nonlinear change. Like you can test the extent to which they level off and individual differences and all that kind of stuff. So, cool.
What was that called again?
Piecewise is the first one. Piecewise, otherwise known as linear splines in a regression context. And in your case, it would be really straightforward because you know that you want to test the break after 15, but there are other versions of the models where one of the parameters to be estimated is where the break is. It's a way of addressing nonlinearity. So that's what that sounded like to me. Thank you for sharing. Anyone else want to play right now? Okay, if you don't, that's fine. We got a long week together. All right. So why do longitudinal research? It's a lot of work. It's a lot more work than cross-sectional studies tend to be. So here's just some examples of the types of questions that people tend to ask in my experience working with longitudinal designs. So the big one, the one that's the most obvious, I think, is to explore within-person change over time and its relations. So we're talking about different aspects of change then potentially. So on average, which is going to be covered by terms we'll learn as fixed effects in a model. For instance, does my new treatment result in greater change or faster change than a standard protocol? That's your sort of classic randomized controlled trial type of design over time, where the group differences in the slope would be what you would want to know. We'll look at several examples of that type of design tomorrow. But then beyond that, okay, so let's look at the people within a group. They all got the same treatment. Why did some of them turn out better than others? I don't know, individual differences. And the types of variables that can predict why some people change faster or more than others are things that differ between people, between persons, characteristics, things that are measured once. Another reason, which is from my days at Penn State working in an area of cognitive aging, because cross-sectional age differences are not the same thing as longitudinal age changes. And when I was getting into that literature, most of it was cross-sectional. They would do surveys of adults ranging in age from like 20 to 80 and try to make conclusions about what happens in aging, even though no one in the study actually aged. And what's more problematic potentially is if you think about random selection of people, the people who are still around at 80 to be in your study are like the definition of not random, right? They are the survivors. They're the super seniors who are able to participate in research, let alone just be on this planet still. So when you think about like a growth trajectory that's not on the same people across time, it gets to be a little bit squishy. The same thing is true in younger children as well. The other type of question then I'm thinking of within-person fluctuation, or the word dynamics gets thrown around a lot in this context, within-person dynamics. So on average then, as an example, if I sleep less than usual, am I more impatient the next day than usual? And the key idea here is than usual. So I'm talking about within persons relative to my own baseline. I sleep more than most people, but that's not what I'm talking about. I'm talking about than I usually do. And I think we can all say that regardless of what our baseline is, whether you're used to 6 hours a night or 8 hours a night, if you sleep less than usual, bad things happen. Or does it go the other way? If I have a bad day, is it likely that I'll have more trouble sleeping because I'm stressing about all the things I said when I was so impatient? Then we get into those sorts of cross-lag or reciprocal relations. And just as we were talking about with the reading data, in these cases, it's really important to separate out what is between-person patterns in how impatient one tends to be, period, and how much sleep one tends to get, period, versus what is the relative impact of more than usual for a person. The more than usual is the within person, more than other people is the between person. But then you can have between person differences in within person dynamics. Why is it that some people are differentially affected by less sleep than usual? Again, between person characteristics are what you would have to explain that. So these models then get, there's a bunch of different words that get thrown into this sort of idea of this, I'm going to make this gesture for cross-lag, like my x, this x predicts next times y, and this y predicts next times x. They're known as cross-lag panel models or autoregressive cross-lag models, and people tend to do them as multi-level models or multi-level SEM. And I have a couple slides and talks, words about that on the third day for that one. And then another one that people don't often think about because it's a relatively newer twist is this idea of within-person instability, moodiness, inconsistency. One of the objects of a treatment might not be to improve people, but it might be to improve the consistency with which they do something, like medication adherence, for instance, or minutes of vigorous activity per day. Believe it or not, I'm getting my vigorous activity right now. My watch thinks that I work out when I teach because it's all the gesturing. Not to mention having to leave my house and walk to campus, or from the parking lot, I should say. But this type of question then requires something that's known as a location scale mixed effect model, which is a multi-level model we'll talk about in which the amount of variance a person has is itself an outcome. So someone's variability across time is an individually varying parameter to be predicted by other stuff. By the way, on the download package that I put together, there's a syllabus that has a whole bunch of readings on it that are going to be showing up periodically, and I have linked to their DOI pages whenever we get into something that's particularly relevant for those readings. But one of them that's on here that's not referenced in the slide is a former graduate student's dissertation about these sorts of models that was published a few years ago. So, is this making you feel like the neurons are firing with those of you who have data? These are the kinds of questions. Can you think of anything I left out? So a lot of times when people approach me about working on a grant, for instance, with longitudinal data, they'll have specific aims or research questions that say things like, I want to see how X and Y go together over time. Or I want to see how these things are related longitudinally. And it's my job to be like, no, here's your menu of the things that you could mean by that. Now, what do you mean by that? And it takes several layers of questioning before we can sort of get a more specific answer that would be testable. Because how things go together longitudinally could be any of this. And all of this would require potentially different designs, particularly to look at long-term change versus short-term fluctuation, as well as different analytic strategies. All right, time. So this is something that you will hear a lot about this week, the idea of change over time. Sometimes it's not as obvious as others as to what time should be. So for instance, if I'm looking at grade school children and I want to measure their change over time in something, what should time be? If it's an academic outcome, one would think the grade that they're in or the point of the school year that they're in would be relevant because everybody's learning the same things at roughly the same pace. If it's something like a biological outcome, like symptoms of puberty, then what grade they're in is probably not as relevant as how old they are. And it could be both. There could be different effects of grade in children who start school early or who start school late. So both of those things might be relevant at the same time. In the context of disease progressions, time since diagnosis. So if I'm examining someone's progression of Alzheimer's disease, how old they are may not be as important as where they are in that disease progression. And so time relative to that type of event would be more useful. And within person fluctuation studies, it's not always the case that time is relevant, but it could be. So things like time of day. If you're going to be measuring cortisol, shout out to my psychology folks over here on the right-hand side of the room. I know very little about cortisol, but what I do know is that it spikes 30 minutes after you wake up and then it declines slowly the rest of the day, and it's bad for you if it doesn't decline. Is that accurate? Okay, good. I'm a health psychologist today. And so you can look at changes as a function of when they got up in the morning in cortisol. But there may be other variables where what time of day it is irrelevant. So if I ask how stressed you're feeling right now, you could be stressed at 8 a.m. or stressed at 5 p.m. or anything in between. If I ask how stressed you are every day of the week, has anyone seen the movie Office Space? I'm dating myself a little bit. You need to see it. To the YouTube, after this workshop is over, educate yourselves. But there's a person in there who is commenting that a coworker sounds grumpy, and they say, sounds like someone has a case of the Mondays. Case of the Mondays, kind of self-explanatory. It's Tuesday today. We do not have a case of the Mondays in this room. Happy garbage day to those of you who've been in class with me before. That's a recurring joke, that the only way I can tell whether it's Tuesday or Thursday when I show up to work is if it's garbage day. But it's not garbage day today because we had a holiday, so joke's on me. But anyway, if I wanted to make sure that whatever relations I was looking at between bad mood and feeling crappy and all those things, I'd want to control for whether it's Monday. Because the fact that it's Monday is not theoretically interesting to me, but it's an important source of variance that I'd want to make sure that my model accounts for. Likewise, back in the world of daily diaries, where before smartphones, there was a longitudinal study that I was privy to at Penn State, where they called you on the phone each night. And they asked, did anything stressful happen to you today? And if you said yes, you got 12 follow-up questions. Well, by the end of the week, people had figured this out, and they're like, nope, no stress here, I'm good, thanks for calling. And so you see this like magical decline in stress over the course of the study, which again, not theoretically meaningful, but something that you'd want to control for. Yeah, we call that lying, things like that. So we have to pay attention to time regardless of what kind of longitudinal design that we have, but which aspects of time we need to pay attention to is dictated by the context of the sampling. It gets really tricky when time varies both between persons and within persons. So these are what's known as accelerated longitudinal designs or sequential cohort designs, where, for instance, you start out and you grab first, second, and third graders, and you measure each of them over 3 years with the goal of eventually stringing that whole growth curve together. Well, that's a great idea to save some time because then you end up with like 6 years of occasions with only 3 from any individual. But what can happen is, are this year's first graders meaningfully different than last year's first graders? Could be, particularly if the school mounts some new initiative to help improve their reading per se. Then you're like, oh crap, I have to control for that because that's a between-person difference in what I'm calling within-person time. Question from the chat, does change versus fluctuation relate as to balanced or unbalanced? Usually, but not necessarily. That's like 2 slides from now, so I'm going to get there in just a second. If there are between-person differences in time, the model has to have that in there. And if there's more than one kind of time, the model has to have that too. So in studies of cortisol, it's common to take multiple samples of cortisol from a single day so that you can trace that curve, and then do that over repeated days. So then I have time of day stuff in the model that needs to be there, as well as which day it is stuff that needs to be there. And that would merit a 3-level model, most likely. That's Friday. Yes. And then the last one. Oh, I lied to you, Nathan. Balanced and unbalanced is on this slide. Can you tell I put this stuff together last week? I don't have my slides memorized yet. Balanced is my word for when there is a common measurement schedule that everyone shares. It doesn't mean that everyone has to have every occasion, though. It just means that the set of possibilities is finite. So if I have a study where I'm looking at baseline, and then after treatment, and then follow-up, and everybody has those 3 occasions and they all mean the same thing, then that's balanced. I can use whatever occasions I have from a person. So if they don't come back to follow up in the models that we're going to talk about, I can still use their baseline and their treatment. Unbalanced is when people have a different potential set of occasions. So if I said something like, think of the best 10 memories from your childhood and tell me when they happened to you. We're not going to have the same set of occasions. Even if you had a memory as a 3rd grader and I had a memory as a 3rd grader, that's not the same 3rd grade experience. So EMA designs where your phone beeps you randomly throughout the day lend themselves to this, because the whole total set of possibilities is going to be different across people. Unbalanced data are trickier to model. There's fewer options that are off the shelf. Doesn't mean you can't do it, it just means it's a little trickier. So it seems historically to me that within-person change studies tend to be balanced because you're collecting time occasions deliberately, and the interval that you choose is however much time you think it should take for change to happen. And so people tend to be on the same schedule with those, but not necessarily. So if I had let's say I did a retrospective study out of a hospital database looking at dementia progression, I'm not going to have everybody neatly 1 month later, 3 months later, 6 months later. It's going to be whenever they happen to come in for whatever problem they had. That's unbalanced, even though the objective is to measure change. So balance versus unbalanced controls what choices we have in terms of the modeling. Okay, did that help answer the question in the chat? Okay, other questions? Things you're thinking of? The one, does plan missingness design fit in here? Yes. That would be, I think, at most times an example of balanced, where deliberately not everybody gets every occasion. But the total set that's possible is the same across people. Those are very tricky, because you have to have enough overlap to be able to stitch it all back together again. And there's a whole literature on that, in fact. All right, other questions? Then, getting to models. So how are we going to do all this? A key guiding principle when I describe longitudinal models is to talk about what happens on each side. This is my way of talking about it. And all models have 2 sides. There's what I call the model for the means and the model for the variance. The model for the means, I guarantee you, is what you're used to thinking about when you think of what a model is. What are my outcomes? What are my predictors? Do they have main effects? Do they have nonlinear effects? Do they have interaction effects? Like, how am I going to answer my questions with my predictors and my outcomes? That's the model for the means. Question. In an EMA design with a set protocol, 14 days at random intervals, how does that work with balanced and unbalanced? I'd call that unbalanced, because if it's random intervals, you don't know when anyone could be sampled. I'd call it unbalanced. In practice, though, if it ended up that you had enough commonality, then you may have some overlap in which occasions people get measured, but it's not the full, like, sort of possibilities being limited. Okay. All right, so model for the means, predictors, fixed effects. So when I teach, I just finished doing intermediate, which is our Introduction to Linear Models course here. I use the word fixed effects from day one because I know this is coming. A fixed effect is a slope or an intercept. So if I said this fixed slope is 2, you would know that For every unit increase in x, y goes up by 2. The key idea here, though, is that 2 is a constant, and it is a constant that applies to everyone. It's fixed. In contrast, the model for the variance will contain terms known as random effects, which is the opposite of fixed. It means everybody gets their own. Residuals, or if you want to sound fancy, you can call this the stochastic part of the model. Stochastic means error, by the way. And error and variance are the same thing. Now, I say that because it was a major epiphany in graduate school when I realized that. Error and variance are the same. Because I had taken ANOVA classes, and we had talked about within subjects error and residual error, and error meant you screwed up your experiment. And then we went to regression, and it's like, no. Individual differences, it's variance, it's cool. But variance is error. So we're talking about that part of the model, whether you think about it as, why didn't your model get this prediction right? Why are you off this much? Or, I'm off this much because I'm different and special. I'm variance. Either way, same diff. Another question from the chat: in the situation that students could share the same pretest, but they would be routed on their performance into different subsequent tests, is that unbalanced? It's heading in that direction depending on how many possibilities there are, I would say. But as long as there's still the same possible set, I would say that's balanced but incomplete. Unbalanced is like, I don't know when you're measured, it could be anything. So this idea of what else needs to be in the error part of the model is the primary way that longitudinal models differ from cross-sectional models. In brief, we will have a different type of variance or error term for every distinct dimension of sampling. So we have differences between people as one type, differences within people as another, between person differences and within person change as yet a third. So it gets very complicated very quickly. But this is how the models differ from what we would think of as a typical regression type of model, where all we're focused on is the fixed effects. Okay, so how are we going to model all this idea of differences between people and within people at the same time? That's where we're at here. So questions before I move on to that? More questions, I should say. Thank you for typing them in the chat. And if you don't want to ask a question to everyone, you can send it to me directly in the chat as well. That would be fine. I've gotten a lot more questions since I've had that possibility in my classes. Yes, sir?
Yeah, do we have any kind of restriction with respect to the outcomes we can gather or collect in this kind of studies?
No. But the type of model that you would need depends on whether your outcome is conditionally normal or whether it's some other kind. Yes, in theory, no. But in practice, yes. Well, certain choices are not possible for certain types of outcomes. Can I repeat the question from the rumors? Yes, the question was, can we do these models on any type of outcome? Is that a good rephrasing?
Yeah.
And the answer is yes, you can. But the choices that you have are going to be more limited for outcomes that are not conditionally normal, so that head outside the realm of general linear model regression land. Okay, other questions? Okay. No problem. So then how are we going to introduce all these additional sources of variance / errors? And you'll hear this described with the word dependency. And that word to a statistician means a problem to be solved, but to a developmental scientist means an exciting thing to explore. Dependency is correlation. So the idea is that observations taken from the same sampling unit are going to be more related than observations that come from different units. Always. From the same day, from the same person, from the same company, same classroom, whatever. If we ignore longitudinal dependency, if we pretend that we just have separate independent observations, if we ignore it with respect to the outcome, that's a well-known problem. So nowadays, you would be hard-pressed to get a paper published in any journal on longitudinal data if you just pretended your data were cross-sectional and went ahead with the typical model. Like, people know that this is a problem. And it's not just the standard errors in p-values. The problem also comes in when your predictor variable is measured repeatedly, because then you end up with the wrong answers. So if I have a regression model, for instance, looking at the amount of sleep predicting one's impatience, as the example I gave earlier, then there's at least two ways that those two things could be related. People who tend not to get enough sleep might be more impatient than other people. That's between persons. On days when I sleep less than I should, or that I'm used to, I am more impatient the next day. That's within persons. And if I fit a single regression model where I just have sleep and impatience, the answer that I get back for that slope is going to be a smush of the two, what I refer to as a smushed effect. Literally, that's my term. I put it in the index of my book and everything, because you're smushing together these two different layers of information into one slope. That slope can't possibly be right, except in the very, very rare occurrence in which the slopes are actually the same. Because we're talking about unstandardized slopes on different scales too. So what do we do about this idea that observations from the same person, first to start with, are going to be more related than observations from different people? Here's 3 strategies. Fixed effects. Can I just control for person and just like set that aside, not do anything with it? Yes, you can. And in certain fields, this is the preferred way of doing business. So I'll go through each of these in more detail in just a second. Fitted multivariate model with some kind of alternative covariance structure besides independent. So just let the dependency be there, let the residuals be correlated, the end. Or at a level. So what level means is another type of variance being introduced into the model that's known as a random effect. It's also known as a latent factor. So the same type of solution is available across what I would call multi-level modeling frameworks and structural equation modeling frameworks because of this equivalence. So the first one, fixed effects. You would literally take person ID as a variable in your data set and turn it into a categorical predictor in your model. That would fit n-1 dummy codes for your sample, where n is the number of people, -1 because you already have an intercept. Or you can kick out the intercept and put in all n. So then I would have a separate mean for each person to start with. If I also added to control for dependency related to differential change over time, which is a separate thing, then I could put in person ID by time interactions. Again, n-1 of them. That would completely saturate the model with respect to why people differ from each other, which is both good, if that's what you want, and bad, if that's what you don't want. So if I put in which person ID you are, and you're person 1, 2, 3, 4, 5, 6, all the way through 30, I can't then look at individual differences because I don't have any. The ID variables took care of that. So when you might want to do this is if you actually care about the particular individuals. So if you're doing like what's known as an N of 1 randomized control trial or single case designs, and you have maybe 5 single cases, then you might want to pool the data, estimate a model on all 5 people, but control for who's who. So you can talk about what happened to Bob, and what happened to Mary, and what happened to Lisa, and all the people, not me, the other one, since she's in the audience today. And so then you would limit your conclusions to these particular individuals, even though they differ from each other in a million ways that you haven't measured. So if that's what you want, then this is what you would want to do. But if you want to predict why people differ from each other, and you have the sample size needed to do so, then this isn't going to help you. By the way, there's a debate in the econometrics literature about fixed versus random effects. And there's a test that you can do as to whether or not you can get by with random effects or whether you have to do fixed. And that test is mathematically equivalent to whether or not you have a smushed effect of a predictor across multiple levels of analysis. So it all kind of comes back together, and I have a couple readings on that I can send you if anyone's interested in that particular aside. So we're not going to do this, but it's an option. Number 2 is just let the residuals be correlated. What's the big deal? And if you have balanced data, you can do this. If you have unbalanced data, you cannot do this. If you have a regular outcome whose residuals are supposed to be normally distributed, and if that's a plausible thing, you can do this. If you need a generalized model instead, meaning like you're predicting a binary outcome, a count outcome, a zero inflated outcome, a skewed continuous outcome, is something that isn't conditionally normal, you can't do this. Because in a lot of those alternative models, there is no separately estimated residual variance. It doesn't need it, only the normal distribution needs that. And if you don't have a residual variance, you don't have residual covariance or correlation that's possible either. So when would I do this? If I had something like pre-test, post-test, absolutely I would do this. And I would like skip the rest of the whole course. Be like, here you go, this is all you need. I have a couple examples of this type of design tomorrow. So this is where we get into the classic repeated measures ANOVA type of model. There's absolutely nothing wrong with ANOVA. What's wrong with ANOVA is that when people say ANOVA, most of the time they're talking about ordinary least squares estimation of the ANOVA, and that's the problem. Because in order to calculate sums of squares within and between and total and all that stuff, you got to have all the data. Can't have missing data. Good news though, that's not true if you switch to likelihood estimation. So there's two kinds of ANOVAs that you would see in this context that are relevant. The kind that I learned as just repeated measures ANOVA, and it wasn't until grad school that I heard about another kind. Univariate, the idea that we have equal variability across the repeated types of outcomes and equal covariability. That's consistent with the idea that all we have to do is hold people constant by controlling for mean differences, and then we're good to go. That is rarely going to be the case. The multivariate approach instead says, let's just not make any assumptions. Let's just let each outcome across time have its own variance, have its own covariance. We'll just let it be. Can't be wrong. It gets to be difficult to estimate when you have a lot of outcomes. But again, something like 2 occasions, 3 occasions, I would do this in a heartbeat. Just do the multivariate approach and be done. So switching to likelihood estimation is going to be a big deal. It allows us to use all the occasions we have that are complete. It's not magic, but it does prevent us from having to throw out whole people in some circumstances. And by the way, if any reviewer tells you, you can't do a multi-level model on 8 people, I'd be like, I just did. And in fact, I have. There's a couple papers my name's on with small samples like that. But one of the arguments that they said is that, well, you can't do that because it's likelihood estimation and that requires big samples. No. Residual maximum likelihood is a special flavor that is mathematically equivalent to ordinary least squares if you have complete data. So if you would have been okay with me doing a t-test on my 8 people, you got to be okay with me doing a multi-level model too, because it's the same machinery either way. So once we switch over to likelihood estimation, not only do we get to keep partial data, but we also have more choices as to what the pattern of dependency might look like. And so then we get into things like compound symmetry heterogeneous, where the correlation over time is the same, but the variances change. Or all these things you may have heard of, like autoregressive models, or moving average models, or autoregressive moving average models, or topolets, or anti-dependence, or all these types of patterns that you can choose from. That's all possible through the use of likelihood estimation. Okay, now the third one, add a level. So none of the things on the previous 2 slides have dealt with adding random effects. I can use fixed effects, or I can just let the residuals be correlated and have different variance. That's no problem. The third one is the one that probably is going to be most useful most of the time, because you can do this regardless of whether you have unbalanced or balanced data, and regardless of what kind of outcome you're predicting. So adding a level means adding a random effect to the model. Random effect is a term that each person gets their own of, like their own intercept, their own slope for change over time, their own slope that describes their relationship between sleep and impatience. Random. Everybody gets their own. What we estimate directly, though, is not the random effect for each person, but their variability across people. So between person differences being explicitly built into the model. That, in turn, induces variances that change over time if it's a random time slope, as well as covariance that changes over time. So this is a general strategy that will work in more cases. So what I would define a level as is each dimension of sampling that has unexplained outcome variability. And you would have a set of random effects potential for that. So what do I mean by unexplained? Let's say that you have a study where you have a control group and a treatment group, and you follow them both over time. So you might think to yourself, wait a minute, is that time and then people and then group? Do I need to worry about group? Is that like a 3-layer level model? Layer and level are the same to me, by the way. This is the hand gestures here. This is the part that isn't captured on YouTube, is all of my wonderful supplementary gestures. You know, this is your tax dollars at work right here. The answer is no, because if I only have one control group and one treatment group, once I put that group dummy code for who's who in the model, I have controlled for group. We're done. Then people are supposed to be independent. Now, what if I had a study that spanned multiple sites? I couldn't get enough patients at one site, so I went to multiple hospitals, multiple cities, and whatnot. Then if I had, say, 10 treatment groups and 10 control groups, if I put treatment versus control in the model as a predictor, I'm not done. Because that would assume that all people are independent, but they're probably related based on which particular control group they were in or which particular treatment group they were in. Especially if your subjects are not equal across all the sites, right? There's different communities with different populations. There's going to be a lot of unexplained variability for reasons that have nothing to do with your treatment or your control. So in that type of circumstance, you would actually need 2 additional levels, one for person and one for group. And each of those levels could have its own set of random effects, ways that it differs. So people can differ from each other in intercepts and slopes. Groups can differ from each other in intercepts and slopes. So it's like a set of differences that pertain to different types of sampling. So in EMA designs, for instance, as another example, if I have multiple observations within a day, multiple days, multiple people, that's another 3-level design. 2 layers of random effects would be necessary for that. Okay. And if you're thinking, okay, how does this work with other names of models that I may have heard? Here's a taxonomy for you. So I will try to avoid a lot of this terminology, but I wanted you to see it so that you can see how it's related. So we have general linear models versus generalized models. Those are for cross-sectional data. Those are models that assume independent samples. And the difference is whether or not you're predicting an outcome directly and saying that it has a conditionally normal distribution, or you need to predict it through something called a link function. So if you've heard of logistic regression or Poisson regression, multinomial regression, these are generalized models. So the word general means normal, and the word generalized means not normal, generally speaking. What we're talking about is introducing this additional word to the party of mixed. Mixed means fixed effects and random effects. Mixed effects means the same thing as multi-level. And we can do, to speak to your question, Vladimir, any kind of outcome we want. It's either general or generalized, based on what kind of outcome it is. And then if we have additional layers or levels of random effects that are needed, then it turns into the mixed kind. So if you pick up a book written by a statistician about longitudinal analysis, such as the Walt Stroop book, it is called Generalized Linear Mixed Models. Like, that's the name of the book. It's a good book. It's a hard read in parts, but it's a very good book. I am focusing more on the general linear mixed models for this week because that's enough. But rest assured that whatever kind of outcomes you have, there's a way to address them in longitudinal analysis. All right, so more word salad then. If we're getting on the topic of synonyms, the same model could be called about 8 different things depending on where you're reading it, who made it, and how they were trained. That has fixed and random effects. So intercepts and slopes are specific kinds of random effects. You might also hear that called a random coefficients model. And if you were trained in education especially, you might hear this called HLM, or hierarchical linear models. Those words are all the same. They refer to a set of models that have fixed and random effects. Not to be confused with hierarchical regression, which is when you have a regression model and you build it in layers. That's not the same thing, even though the words are very similar. So special cases of this one sort of overarching idea: random effects ANOVA or repeated measures ANOVA, as we've discussed. Growth curve models. So the word latent you can use if you want to sound extra fancy. Within-person fluctuation models, also dynamic structural equation models fall into this category, or what's known as multi-level structural equation models. If you're not talking about longitudinal data, we get into clustered observation models. And if you have a longitudinal study of people in groups, then that's clustered longitudinal. The term value-added models is sometimes popular in education. It's the idea that we are going to track individual teachers in terms of their student outcomes. That is accomplished by something that's known as a cross-classified model, or crossed random effects, where you would have random effects for students and random effects for teachers at the same time, and potentially fixed effects instead. And last but not least, any psychometric model. So if you have items nested in people, that's not different than occasions nested in people. So if you're taking classes in my other fall class, besides longitudinal, will be SEM, learn about factor analysis, item response theory, which is factor analysis on binary and categorical outcomes, and the world of structural equation modeling. So honestly, it's all kind of one big amorphous thing, because random effects are the same as latent variables. So there's a lot of instances in which it's the same idea and the same underlying machinery, but the words and the notation look very different depending on where you go. Question: how do I know what level to group them in? For instance, I have reading teachers that individual students are in, but they are getting the intervention from a tutor. Oh, great question. So there's not a ready answer, but I can tell you this. If you're not sure what's nested in what, your data are not nested, they're crossed. That's my answer. So you may have a situation where the same student is associated with a teacher and a tutor. Those can be crossed random effects at the same time. The same would be true if you had, say, an intervention design where people could show up to different groups as part of the intervention. Like you could show up to like an AA meeting at this church on Sunday and an AA meeting at that church on Monday kind of thing. Then people in groups are crossed, they're not nested. And it changes the way that you have to think about the model, but the same principles still apply. You can still predict why some groups improve differently if you have enough people who attended it like all the time, so that you can get different group differences and change. But I'd have to answer the question on a more specific basis to tell you how do I know. I have a little bit of that on, I think it's the end of tomorrow, about 3-level designs and where time is, because time isn't always at the bottom. Okay, 10:02. How are we doing? Good? Hanging in there? Do you want to hear about random intercepts and then maybe take a break? Does that sound reasonable? Okay, cool. Zoomers, hanging in there? Excellent. Love to see the thumbs and the faces. All right, so back to models then, to be a little more concrete. So this would be an example of what I'd call a general linear model, or what most people would call regression, where I've got one outcome being predicted by the model for the means, which is the red part here, the fixed effects, and then the model for the variance, which is at the end. So in terms of notation, it's y sub I because each person has one y in this model. It's x1 sub I, x2 sub I, and e sub I for the same reason. There's one per person. Subscripts are everything in these models. What the variable varies over has to be part of the equation for it to make any kind of sense. But note beta 0, which is my fixed intercept, which would be the expected outcome when all my predictors are 0. Beta 1, which is the slope change in y for a 1-unit change in this x and that x. These don't have i's because they're constants. They're fixed effects. Everybody gets the same number that multiplies their variable. So we're focusing on the end here. What else do we need besides e is the question. if we had multiple observations per person, how does the model have to change to adapt to that? That's what we want to look at. So just to get a few pictures in here to go with the equations, let's say that I have this pile of cross-sectional data, a histogram turned sideways, and I start with what's known as an empty model, or an empty means model more specifically, because we're talking about the model for the means. So just beta 0, hanging out all by itself. Now you would typically not ever do this in regular cross-sectional analyses of regression, but this is the starting point for everything in longitudinal. If I don't know anything else about a person, what's my best guess for their outcome? The mean. That's kind of where the term model for the means comes from, is because it's not just going to be one mean. Each person gets a custom mean based on their predictors, but anybody who had the same profile of predictors would have the same predicted mean. So it's a conditional mean instead. So yeah, I'd say the mean for this sample is 90. For this particular person down here, this is not a great prediction for them. So they're off by minus 58. But we don't really care about each person's residual, the E. We care about their variance across people. So we would have one number that summarizes how people differ from each other, where the differ is relative to just what the mean says. Now, what if the story changes to make it longitudinal? Now, let's say that I've got 5 occasions apiece from 3 people. So I have to switch my subscripts now from Y sub I to Y Ti. T is for time, I is for individual. And in contrast to what I saw in Snyder's and Bosker and other classic textbooks, you don't have to pick IJ. It is not a rule, I swear. You can pick whatever letters make sense. So I tend to do TI, T for time, I for individual as sort of a generic. But if you have like days within students, DS. I don't tend to pick O because it looks like 0, and that gets confusing. I would do O for occasions otherwise, but T for time works for that. So I would encourage you, when you're writing your own stuff, pick letters that mean something. It will help people stay with you. So let's say that I have hypothetical longitudinal data that looks like this. It's of the fluctuation variety, where there's no change on average. That's indicated by the black line here, but I've got people who vary around their levels across time. If I fit a classic general linear regression model designed for cross-sectional data, the way that I would think about the E that goes with each person's observation at a given occasion is that it has to represent all of the discrepancy between what the model says via the fixed effects and where this person ended up. So this purple person is below average all the time, so their E's would always be negative. And because they're below average all the time, these E's are going to be related to each other. So we got to fix that. We fix it by splitting it. So to account for the fact that this person is lower than other people on average, I'm going to put that in the model. That, being lower than average, is captured by this U0I term, which is called a random intercept. The 0 means that it goes with the idea of beta 0 as an intercept, and I, because each person gets their own. So if you are below everyone else, your U0 would be negative. If you're above everyone else, it would be positive. So once I give each person their own U0, that's like giving them their own mean. And then E swoops in to fill the gap of what's left. So E then is the difference between the person's mean and where they actually are at each occasion. So I've taken what used to be one pile of variability, and we're going to split it into 2. And in so doing, U0 now predicts a correlation of the observations from the same person. It predicts it to be constant over time, though, because this person is lower than usual. Lower than others, excuse me. That's what U0 is picking up, my random intercept. So to put some more notation on the ideas, I haven't put any predictors in the model yet. This is an empty model. All I'm trying to do is figure out how much variability I have of each kind as a function of each kind of sampling to start with. So each person has their own potential U0I value. We don't care what they are, we care about their variance across people. So the terminology that I use in my book following traditional notation is that the variance of these U0I random intercepts is called tau squared. So random effects have taus as their variances, and I always put as a subscript what it's the variance of. So this is random intercept variance specifically. If I have a design where occasions are nested in people, this is at level 2. So people measured repeatedly would be the story here. So this number that's going to be estimated from data tells us all the reasons why some people are higher on average and some people are lower on average. That's the part that the study would have started with if you only had a single occasion. It's cross-sectional information. So it's inter-individual differences. Why are some people's means higher than others? Don't know. We're going to figure it out. Once each person has their own mean, the e's that are left, that's your sigma squared e that you're used to seeing for e variance, but it's ETI. So it's per time, per person, and this is residual variance at level 1. So I use these terms religiously to try and avoid confusion. If it's level 2, it's random something. If it's level 1, it's residual something, because I'm talking about e variance at level 1 versus u variance at level 2. So then E is purely within person information. Why am I higher today than my mean? I don't know. That's another source of variability to explain. Intra-individual variability. So putting it into an equation then for an empty model would look like this. So the model for the means is the same. I got a fixed intercept in both places. Because my best guess, if I don't know anything else, is the sample mean of my outcome. From there, the model for the variance takes over. U0 is how far off my mean is from the grand mean. ETI is then how far off my observation today is from my person mean. Question?
Yeah, so once you have a 2-level model and you add in the vector of the means for each individual person, you don't have to have some overall level 1, I guess, kind of variance for each individual, because the mean for each person is changing, and so you only need to look at the person within time error. Is that correct?
I'm not understanding you yet.
So like in your first model, right,
Okay.
you just have E sub I,
Mhm.
right, because you just need to look at overall how much error is there, and so once you add in the mu, you don't have to have that just E sub I.
E sub I changes.
Yeah.
So
because
yeah.
it's per person, per time, right?
Yeah, so the question is about whether or not E sub I is needed. It changes what it means. So the total deviation from the grand mean is split into 2 different things. And so E sub I in the first model here, because it's for cross-sectional data, these are differences between people.
Yeah,
U is now differences between people, and
Okay.
E is within people.
got it.
And I know that's confusing, but why it's that way is because in the initial versions of multi-level models for clustered data, people were at the bottom and groups are at the top, and then the E's stay with the people. And so they made it that way with that context in mind. To be able to borrow the same notation in 2-level models, you have to change what E means. But U0 is, the idea of it is, why are some people higher on average than others? And after I control for that, why am I worse today than yesterday? And each of those is a different source of variation for different reasons to be explained by different things. So why is it that I might be higher or lower than other people? People characteristics. My education, my gender, my ability, my lack of ability, how many hours I tend to sleep, all these things that I carry around with me that are traits. Versus ETI, why am I off my mean today? Maybe I didn't get enough sleep last night. Maybe I don't like rainy days. But my education or anything else that's constant can't explain why I'm off my mean today and not yesterday. So between person versus within person, our first demarcation of that. So while it's convenient that this model allows us to separate those different kinds of variance, and indeed the very first thing is figuring out how much of each kind you have, it also, at the same time, behind the scenes, what it's doing is introducing correlation. Because if you left that out, these E's would be correlated. You're saying, no, I'm going to take the correlation in the E's and I'm going to give it a new name and stick it over here. It's called U0. over here is the G matrix, by the way. We'll get to more terminology. But again, starting with ideas. Yeah. All right. Nah, I don't know that we want notation yet. I think we need a break. How's that sound?
Yeah, great.
Yeah, a break before multi-level notation. All right, let's maybe back like 10:30-ish. Would that work? It's 10:14 now by my clock. And if anybody wants to ask questions, I will stay here for just a few minutes, and then I'll take a few minutes away too. So, all right.